Hey, good morning. All right. Boundary layer sciences, physics kind of explanation. Somebody came in and was talking about nuclear properties and kind of made a statement that everything is different when you get into nuclear properties. And I'll get into more in a second about that. So, yes, when you go into subatomic particles, there are a whole new set of particles we are still discovering and trying to understand the physics for. Yeah, that's the land of gluons and muons and 14 other particles. Or I'd have to go refresh my memory, right? So the physics, the equations get different. They become different. If you're dealing in chemistry, this was around bonding. And bonding is all chemical equations, and a part of that is electrons and where those orbitals for the electrons are. They're very specific in a general stochastic kind of way, right? Because when we get into the physics of the particles, those actions are stochastic. But we see the results in that 99.999 things in chemistry work. It's that small nuclear thing out there, that 0.0000 so much percent, that adds a complication into all equations. First, we didn't know about those complications, right? Some of this stuff we attributed to entropy and you know other words for things that degrade over time. As we went, the equations got better for how these things happened. So when you're speaking to chemistry, you use chemical equations. You don't use subatomic particle physics equations unless you have a reason to, unless in the materials you're working for you found decay properties of any. Remember, carbon decays. So if you're doing something, you need to, carbon 14 decays, right? If I'm going to build something long lasting, I don't want to use carbon 14. Where was that in your chemistry equations? You had to add more onto it. So what actually happened at that boundary was all the equations got more complicated. You go from chemistry, you have to add in nuclear decay properties if those materials are there. How would you know if they're there? Well, that's a multi-million dollar question for a multi-million dollar lab. And you might not care if 0.000007% of your chemical reaction does not resolve out. You can call that entropy or whatever else you want, and you might not have to go look for it, right? Because it doesn't matter. Or does it? So where's your black and white decision on this thing? Where is the true and false decision on this come from? Um, it isn't that easy, Steve. So the point of this is it just did not get easier. Did you have some expectation all of a sudden all these answers were in this next level of research? I don't know. I don't know what's on the other side of the Big Bang, but that is where we're trying to get near to look at. And we aren't near it. We just aren't. We are using some of the most sophisticated tools that mankind created for himself to use to explore the universe. And here's where we are. Smoking cigarettes, idiot. So yes, at the subatomic level, all the rules change. All the rules at the subatomic level support the atomic level theories. This is where E equals mc squared broke. And Einstein knew this. And it wasn't broken, it wasn't complete enough. It did not allow for subatomic variables we didn't know enough about. But it worked with all the materials we did know about. We just got better. We've got more decimal places in our toolboxes. Every day we can splice genes and know what some do and have an idea what others do. So again, no hard answer. It's all squishy stuff between your toes that people don't like. And I like squishy stuff because you can wash it off with water.